Week 16, last lecture. When astronauts first went to the moon and took the famous photograph of our fragile Earth from space, it was suggested that a sudden and enormous consciousness shift happened in the human race, helping to birth the modern environmental movement. In Butterflies Are Free, Stephen Davis suggests that quantum mechanics and the new physics are redefining how we approach reality and how our consciousness affects it. He suggests that movies like The Matrix and The 13th Floor and the Star Trek holodeck are the product of a gradually dawning awareness among the public that we may be living in a holographic universe that is more like an immersive interactive video game than any of the previous models of reality philosophers and scientists have come up with. As you play God by creating your sustainable virtual realities using today's tools, how does that affect your thinking about environmental and social change in general? Does collaborative world creation inside VR change the way you think about how to go about change in the outside world? This is Module 4.4, Playing God, Week 16, Thinking Out Loudest, Lecture 4.4. Playing the Superman, playing with the future, opening your vision of sustainability to the world. There is no question that designing future worlds is a kind of Gottesspiel, playing God in German. When thinking out loudest, manifesting our visions of the future in real, tangible ways that can affect other people and other beings' well-being, we must observe the adage, with great power comes great responsibility, from Spider-Man. This lecture helps students work through the implications and ramifications of that power so that they can plan responsibly, so that you can plan responsibly. This lecture is based on a paper written by Dr. Shelnutt, the former director of the Patel Climate Change Mitigation and Adaptation Concentration, and myself and faculty from Florida Gulf Coast University. It is in relation to the Viper Lab for visualization that they have at Florida Gulf Coast and our new Envisioning program here at Patel. Given the state of the world today and the urgent need to maintain water and food security and combat poverty in the face of population growth and global warming, we need to use today's technology in the right way to prepare engineering and sustainability students for the transition. There is a greater level of interest in the impact of the new tools on preparing the next generation of engineers, champions of change. As part of this enhanced learning, virtual worlds or virtual three-dimensional environments are available for education. See Kelton 2008. The timing couldn't be better. Students today are what futurist and former Disney Imagineer Joe Tankersley calls digital natives, unencumbered by our analog history, who are trading in their jobs for personalized careers built around their passions, as dreamers who gleefully share their experiments and invite others to co-create with them, refusing to believe in our economics of scarcity and instead creating a world of abundance, sustainability, and equity, end quote. Tankersley, who's working on the Envisioning Sustainability course curriculum with us at the Patel College of Global Sustainability, suggests that such digital natives, that's you, will not wait for permission to empower themselves, yourselves, and in so doing will empower everyone. He says that on page 9 of his book in 2018, Reimagining Tomorrow. With Forbes reporting that more than half of brick-and-mortar colleges may be forced to close their doors in the next decade as online resources become more prevalent and the digital natives become increasingly skeptical of the need to pay for encounters with live humans who merely direct their attention to digital resources available outside of school classrooms, that's Horn 2018, current models for engineering education need an overhaul. Tankersley, who oversaw teams implementing VR at Disney, remarks that younger generations, quote, move easily between worlds, end quote, and because, quote, knowledge, whether technical or professional, goes out of date at an alarming rate, digital platforms that connect professors directly to learners, created by educators who are eagerly developing methods to meet the needs of learners on their terms, will be the most successful forms of education as the changing job market forces workers to, quote, take more and more responsibility for their own success and empowers them to chart their own futures. That's page 74 of Tankersley. It's the ability of virtual and augmented reality platforms to blend realities together and, most importantly, customize them to the specific needs and locations of the learner that make them so powerful and necessary if institutional engineering education is to remain relevant. Why virtual reality for education? According to Stacie, virtual reality, or VR, is the use of computer technology to create a simulated environment. And unlike traditional user interfaces, VR places the user inside an alternative virtual world. Instead of viewing a screen in front of them, users are immersed and enabled to interact with 3D worlds. VR is dependent on graphics and complex computers that display and coordinate virtual environments, according to Ahalabi 2016. And interactions with these environments requires the use of tools such as gloves, joysticks, mice, special glasses, or head-mounted displays, HMDs, that detect user movements with sensors. Computers are then able to compute and react to the movements by changing scenes. Now, the appeal of VR lies in the ability to create environments that may be too dangerous, costly, time-consuming, or complex to be experienced in reality. And consequently, virtual reality has a large potential in the educational field. Engineering students are able to use VR to examine the consequences of their actions and decisions and practice experiments as often as they would like. This helps to experiment several scenarios and reduce the likelihood of design mistakes. Such educational utility can improve students' performance and capabilities in various fields." End quote. In today's world, engineering students are also expecting institutions to provide them with the appropriate modern industry technologies to prepare them for their respective fields. VR sees use in military training, medical training, applied research, commercial applications, and automotive and aerospace design, according to Abelrub et al. 2011. 3D visualization products provide an indispensable method for showcasing projects and designs and enables engineers to visually experience design ideas and alternatives. 3D virtual reality provides engineers with state-of-the-art technology that will see major use in the current industry. Allowing engineers to experience VR will subsequently strengthen the quality of the industry by adding value, reducing product development time, as well as the product's time to market. In particular, VR is proving vital in the new technology and solutions to the global challenges that we have, where a 3D visualization can be built virtually. In this manner, virtual environments can be reviewed and used to make decisions without the need of a real physical prototype. This reduces development time, costs, and improves product quality. Now, using virtual reality as a tool to educate within the field of engineering is not a new concept. In 1995, Pentelidis proposed the use of VR as a teaching aid, detailing the types of VR available at the time, reasons to use it as an educational engineering tool, and when to use it. Many of Pantelidis' 1995 suggestions apply in the present age just as well as, if not better than, they did decades ago. The question is, are these tools accessible to you here at Patel? And the answer is yes. We have it. And VR enhances teaching various engineering concepts by encouraging your active participation during the learning process, which is of particular importance when dealing with fields as complex as sustainability engineering in the age of climate change. Since 1995, there have been experiments to test the effectiveness of VR-assisted engineering education, and one such experiment involved teaching pre-university students basic civil engineering concepts using VR. This is according to Dinis 2017. Furthermore, it gave learners the opportunity to progress through material at a rate that you are comfortable with, according to Pentelidis 1995. Beyond showing the advantages to using VR in an engineering education, Pentelidis in 1995 offered situations in which VR's strengths really shine. Due to the artificial nature of VR, it allows learners to safely experiment with otherwise hazardous situations, making it ideal for training that involves dangerous environments. It presents learners with the ability to explore situations beyond physical reality, things that can only exist inside of a simulation. Pantelidis in 2015 went on to mention that VR simulations can be far more forgiving than reality when the mistakes that the learner could make have substantial consequences. Stacie says, the food-energy-water nexus is central to sustainable development. The inextricable linkages between these critical domains require a suitably integrated approach to ensuring water and food security, sustainable agriculture, and energy production. However, the analysis of one resource sector is sufficiently complex, suggesting that integrating multiple resource sectors simultaneously poses an appreciable challenge. That is also cited by Deloe and Patterson, 2017. Professor Tsiege and myself and our students in 2019 built a food-energy-water nexus system on campus that turns wastewater and solid waste into recycled water and energy for irrigation. And teaching the complex interaction between water, energy, and food system is still a challenge. So this lecture presents a virtual reality-based water, energy, food nexus visualization and simulation tool for teaching engineering students. He calls it VRWEF, and it's a powerful immersive tool that places students at the center of an alternative virtual world that makes it easy for you to experiment and learn complex food, energy, water engineering concepts effectively, and then understand the consequences of different development paths. The Food, Energy, Water Nexus system that we're developing at Florida Gulf Coast University and here at USF is finding its way onto the map in speculative fiction and planning. The idea of using circular economy, food and toilet waste-based biodigesters as the basis for aeroponics and hydroponic systems has even been featured as a solution to the zombie apocalypse, as I mentioned, in the popular Netflix sci-fi Z Nation and in The Walking Dead. So it is increasingly on the radar for the public. In Chapter 9 of Tankersley's book, called Reimagining Sustainability, Gabby in Paradise, which gives specifics about the technologies that we need to go about reimagining our tomorrows, making sure your future doesn't suck. His character, Gabby, a 13-year-old Latina girl who's living on the Florida coast sometime mid-century and has seen the worst of climate change, visits her friend Dan, who is helping her city planner aunt, Tia Maria, build, quote, another one of her biodigesters that she describes as kind of cool, though, making gas from food scraps and poop. Dan tells Gabby, as your aunt likes to say, you carry enough energy in your gut to power the entire planet. The biodigesters Dan was helping to build, says Tankersley in the narrative, were the perfect low-tech solution to getting rid of all sorts of organic waste. They were just waste composters designed to trap the gas that the decaying organic matter gave off. The gas could be used for cooking or heating, and it was cleaner and less dangerous than any commercial natural gas. Just one of the many renewable energy sources that powered the village where all of the roofs were covered in solar shingles and that didn't get destroyed every time there was a storm. Now, because of the presence of the biodigesters, the hypothetical village described in Tankersley's book has an aqua farm and aeroponics greenhouse that provides, quote, food for the residents and a source of income, and instead of the traditional lawns growing non-native grasses, the village was filled with ground covers that naturally flourished in a salty coastal environment, so that, as a result, there was no need for fertilizers that used to run off into the bay and cause deadly algae blooms. That's Tankersley, page 129 to 131. Now, when students read this text in the USF Envisioning Sustainability course, they often ask, well, where is this wonderful place, this utopia, this village? How can we visit it? Does it exist on any real map? How do we make it a regular feature of our current communities? So what is needed urgently is to start mapping food, energy, water nexus technologies into real-world, not fictional landscapes, to put them on the map both virtually so stakeholders can work through possible scenarios before committing time and money, resources, and land, and then in actual tangible form. And we know this is always done. Professionals in planning and architecture and engineering have long worked with geographic information systems to enable spatial analysis for decision-making that's tied to place, so that the real-world locational data can be displayed in meaningful ways and plans can be made for real-world deployment. But as Yale professor James C. Scott famously pointed out in his book, Seeing Like a State, How Certain Schemes to Improve the Human Condition Have Failed, which I often quote, the map is not the territory, so it's critical to add relevant dimensions and data layers to ensure more accurate representation of the landscape, including cultural, social, economic, and political variables, to say nothing of complex ecological parameters. For this, very sophisticated modeling software is needed, says Scott, 1998. ArcView GIS has been considered the standard for decades. Each new release improves on the last by building the data visualization functionality, such as the 3D capabilities found in ArcGlobe, ArcScene, and City Engine. The company's website extols, quote, "If a picture is worth 1,000 words, a relevant map is worth 1,000 pictures." Use 2D maps and 3D scenes created on your desktop to visualize data in novel ways and discover non-obvious relationships, inefficiencies, trends, and opportunities. That's ArcView 2019. However, the expensive pricing structure students must contend with after they graduate has been a deterrent for many who would otherwise invest more time in mastering its nuances. Students who don't find employment in companies and institutions that have site licenses for these powerful software tools often find themselves discouragingly trapped across the digital divide. And ironically, these are the students whose communities and landscapes of interest often need the most help in redesign and solution seeking to stave off the worst effects of climate and landscape changes and habitat loss and environmental injustice. Now, the open source variant QGIS now has much of the same functionality and enables students to do their mapping in a platform that will remain zero cost for their lifetime and will continue to improve over time. But of course, it lacks the support and customer service of the commercial software. None of these mapping tools currently allow for a truly immersive experience, however. While the gaming world is already making more emotive, impactful simulations of green futures, playable to everyone through titles for the PC, Xbox, and PlayStation, such as the City Skylines Green Cities I talked about in the last lecture, that enable players to create a sustainable future, often by playing as the mayor or city planner, with all the food, energy, water, and waste nexus parameters, ecological and economic, budgetary, including trade-offs and political conflict. Players can implement everything from urban wind and solar farms and geothermal heat pumps to EV parking, green roofs, and farmers' cooperatives, and have a nice, ever-expanding menu of green technology choices. The limitations of these hyper-realistic and super exciting games, however, is, as I mentioned, that the green neighborhoods are never located in any real region of interest to students and remain neverland abstractions that at best encourage inquiry possible technologies and cost-benefit decisions that must be made for proper implementation, but that rarely prove useful in improving real environments in the real world. See, education, particularly engineering education today, that wants to remain relevant needs to incorporate the best of GIS programs and MMORPGs, massively multiplayer online role-playing games, and do so in a way that is free or inexpensive and that is accessible and will remain accessible for all students for the rest of their careers and lifetimes. Actually, the software to create immersive real map-based scenarios that are local and unique is already here. With the improvements to cost-free browser-based services like Google Earth and Google Maps and OpenStreetMap, OSM, and the available of open-source 3D modeling and gaming software like Blender 3D with its new Blender GIS plugin that enables use of web geodata from Google Map, OSM, and DEM SRTM data, that's Digital Elevation Map, JPL, NASA Shuttle Radar Topography Mission data, and free-to-use world-building software such as Unreal Engine, Unity 3D, and Roblox Studio, students are beginning to see that you can do better than 1,000 pictures by mastering these cost-free tools to create your own truly interactive, multiplayer immersive simulations of your own local topographies and communities so that you can play through scenarios relevant to you and your futures in real time. Scenarios that include the cultural, psychological, and emotive content that open-world gaming with real-time multiplayer functionality brings to the table, and make better system thinking, nexus thinking decisions based on the impressions of a multitude of stakeholders. Tankersley predicts that once, quote, almost anyone could afford access to the great data stream, the digital divide that we have been building will start to crumble as cheap data helps jumpstart the micro-entrepreneur movement and access to precise data focused on a local population, quote, becomes a powerful tool for discovering innovative solutions to problems that had once seemed intractable or at the very least unprofitable, end quote. Most importantly, he maintains, they give those communities, quote, the power to imagine their own futures rather than forcing them to accept solutions that lack connection to community traditions and values and left too many people feeling like their only choice was someone else's future or their own crumbling past, end quote, Tankersley, page 90. He says, quote, the great disruption of the digital age was to make us all realize that every future is local and unique. empowered by the tools that make bottom-up change possible, and fueled by the millennial generation's newfound embrace of community and tradition, local solutions spread. To those who are creating community futures, tomorrow seems less like a giant leap into the unknown. Tankersley Ibid. Now, Siege says, research in virtual reality in education is a relatively young field, but in recent years, it has shown considerable growth. Recent examples of the application of VR in undergraduate education have focused on the potential of interactive and immersive displays in order to make the interface for the learning experience easier and more natural to students. The development of an interactive and immersive technology inevitably has an impact on all aspects of undergraduate and graduate education. Students like you would be able to experience a fully immersive experience in simulating and interacting with the food, energy, water system in a virtual environment, which may encourage you to engage in deeper learning. And I've argued that for both the virtual reality food, energy, water system and the ETI field scale system that we built at Florida Gulf Coast to have relevance, students need to be able to manipulate parameters that mirror realistic interventions in another layer of reality, the application space of community and household regional resilience planning. Now, one of the problems of lab bench projects like we're doing at ETI is they don't easily scale up to the field. One of the problems with controlled field study projects is that they don't always scale out properly to environments where there are social, cultural, or political challenges. Ironically, in a properly gamified multiplayer VR simulation, one can actually get better verisimilitude with respect to the broader social and environmental dimensions than in the lab scale or field tests. For example, how do the aesthetics work for a neighborhood, for a homeowners association? How would the food, energy, water system integrate with existing water, energy, and food infrastructure in the community? What are likely risks regarding spillage or leakage or fluids or gases? How might the food, energy, water system be impacted by or impact local wildlife or domestic pets or insects or potential pests? Would there be odor issues or delivery management or operation and maintenance issues to contend with? Our virtual food, energy, water system might be better for answering some of those questions or for heuristically revealing new sets of questions that a lab or field trial may not elicit. But to make the virtual food, energy, water system impactful and truly interesting, students need to know that there is also an actual analog version in the real world that can solve real problems. Otherwise, the intervention seems merely theoretical at a time when there is an emergency, an urgency to implementing food, energy, water solutions to impacted communities. What the combination of the field food, energy, water nexus system and the virtual reality food, energy, water system can do, once we develop the game so that it can be scaled up and down and placed in situational, in situ context with real communities of interest, is enable refinements and tweaks of the virtual and field test models so that we can achieve the proper blend between what Scott 1998 calls techne, codified, easily transferable formal knowledge, and metis, intensely local genius that is uniquely situational. But to make the real field food, energy, water system at the ETI field lab at Florida Gulf Coast University and the virtual system in their Viper lab serve that blended function for community application, we need to make both experiences available to the widest possible audience, and in particular to potential stakeholders who would be interested in applying and implementing the technologies as they mature to their own neighborhoods. One of the challenges we faced at Florida Gulf Coast and USF is making the simulations accessible to a wider public and enabling real-time interactivity by users who are not able to access either the field location or the Viper lab. Over the years, we've experimented with sustainability meetups in platforms like Second Life and VR Chat, but the cost structure of developing permanent VR real estate has deterred full development. Since dedicated servers are so expensive, we turn to other cost-free platforms that enable students to build the food, energy, water nexus systems in geographically accurate landscapes and engage with each other and the technologies from wherever they may be online. The most promising of these so far appears to be the online kids gaming and world creation platform, Roblox, a Minecraft-type open-world sandbox whose online community has already created and made available many of the sustainability elements, windmills, solar panels, tanks, plumbing parts, that we need for our application, and they've also made available the programming for interactivity with fluids and particle effects. In Roblox, we can place our few models and immediately publish to the web, and enable students from FGCU and USF, and indeed around the world, to meet up and start working with the simulations immediately. What is even nicer is that the platform allows team editing, so that multiple students can meet in Roblox Studio and cooperatively change the landscape and build in new models, terrain, and functionality using a kind of Google Docs approach, but in a 3D landscape. The latest release seamlessly accommodates the Oculus and HTC Vive VR experience. Now, there are a few challenges that we'll face in our efforts to implement the VR View Nexus until we can close the current digital divides that seem to force a gap in understanding and motivation between those who've been able to afford the hardware, the software, and time to become digital natives, familiar with gaming as a tool for content learning and instruction, and those for whom this is a foreign and intimidating experience. Without strong leadership and guidance, it's not immediately clear that engineering or sustainability students will be able to realize the promises offered by this new educational paradigm. It isn't a given that digital natives themselves will immediately see how to apply their familiarity with digital tools to the educational arena unless we create the right context for them that can make them excited about the connections between real-world education and escapist gaming. Game designer Jane McGonigal, in her books and TED Talks, has stressed that young people are making a mass exodus away from school and reality, which she calls broken, precisely because the way we teach doesn't offer them much hope for the kind of tomorrows we're creating on their behalf in which they don't feel they can meaningfully contribute to. That's from McGonigal 2010. To achieve the epic win that McGonigal says young people are demanding, they need to be empowered with skill sets that can act as a bridge between super better fantasy world creation through digital imagineering and reality fixing through real world engineering. Even most hardcore gamers don't seem to know how to actually create relevant worlds that can help meet skill acquisition goals. They can be adept at building complex bases and shelters and crafting tools in sandbox games like Minecraft, Fortnite, and Rust, and Ark Survival, and even Roblox Building, but they have no idea how to apply those skills to bringing their own school sites, communities, neighborhoods, or homes to life. The foundational skills of digital engineering for 3D simulation and VR are lacking in most sustainability programs, as are many of the real-world engineering skills and tool use trainings. Minecraft uses Python, Unreal Engine 4 uses C++, and Unity uses mostly C# or JavaScript, while Roblox uses Roblox Lua. Conceptually, the use of these languages is very similar, and one doesn't need to be a highly qualified coder to use programming objects to make a functional game. But sustainability education still sees basic computer programming as a specialized skill rather than a core capability. And meanwhile, the translation between text coding, visual programming, and object creation, functionality scripting is being increasingly taken over by artificial intelligence and machine learning. At some point soon, these divides will be crossed, if only because a new crop of digital natives are growing up with free digital design tools and free online curricula and video tutorials that enable quick creation and instant feedback with AI that takes a lot of the burden off the creator and enables spectacular results. As the Roblox education site says, quote, "Educators, Roblox's creation tools and educational content are provided free of charge. As one of the fastest growing resources for educators, Roblox allows anyone to build and publish their own games while learning real 21st century skills. Students, anyone can build a game on Roblox. It doesn't matter if you're new to coding or you've never designed your own virtual world. With a little imagination and the right tools, you're already well on your way to taking the first leap into game development." What we must do in our schools is enable these powerful tools to be used in the local context and with an aim toward mastering the content of sustainability and the food, energy, water nexus with zero waste circular economy goals. We must empower our students with ways to reward their investment of time in applying gaming technology to sustainability goals and relieve them of the anxiety of having to satisfy both traditional assessment requirements, quizzes and exams that demand rote learning and memorization, and portfolio assessment demands, where a time-consuming and often cooperative creative product is required. As educators, we must also create focused tutorials that are content outcome driven and relieve the students of the burden of having to stumble blindly through a bewildering landscape of menu options, techniques, and multiple software packages in order to achieve desired results. Since the goal is to have productive stakeholder-driven conversations about realistic simulations and alternative scenarios for the sustainability of their futures in their locales, our food, energy, water tool environment needs to be developed in such a way that it provides a heuristic for asking the important relevant questions about landscape change and infrastructure decisions, and be able to visualize different outcomes based on parameters that can be interacted with and manipulated until everybody is satisfied with the results. VR gaming hardware and software allows for such precision and accuracy, as well as for flights of fancy. It's our goal to bring all of these worlds together to create a new form of education that inspires involvement by seamlessly blending the virtual and the real. Let's just do it.